You have probably experienced this. You adjust a date range on a web dashboard to pull up a custom report, and everything stops. The browser locks up, the loading wheel spins, and the application becomes entirely unresponsive. Behind the scenes, the server is struggling to calculate thousands of data points on the fly. We can eliminate this delay by implementing a specific architecture called a prefix sum. By shifting the workload, we drop the time it takes to calculate these queries from linear time, big O of n, down to constant time, big O of 1. To build this, you will need a basic understanding of C++ factors and a code editor. By the end of this exercise, we will write a function that instantly looks up any range of data without crashing. Optimizing this specific mathematical operation determines whether your application scales to millions of simultaneous users or collapses the moment traffic spikes. First, let's look at why the standard approach fails. The most common way to tessellate a range of values is to write a simple for loop that adds each number one by one. This diagram shows what happens when a user queries a massive date range. The loop has to scan the array sequentially. If the user asks for 3 years of daily data, the server has to perform over 1,000 individual addition operations just to answer one request. Now multiply that process by 10,000 concurrent users making similar requests at the exact same time. The server CPU maxes out, and the database queries queue up until the system times out. That linear relationship, where the time to compute scales directly with the amount of data requested, is why loops are a liability during live user queries. We have to completely remove the loop from the calculation phase. We do this using a prefix array. This diagram displays our short input array of daily data values on top, and an empty, identically sized prefix array directly below it. We use this second array to perform the heavy counting in the background before the user ever requests a report. We populate this new array by creating a rolling sum. We move left to right, adding the current day's value to the accumulated total of all previous days. When a user eventually asks for a specific date range, we don't need to add the individual days together. We simply isolate 2 values in our prefix array, the accumulated total at the very end of their requested range and the accumulated total immediately before their range began. We take the total at the end of the interval and subtract the total from right before the interval started. The result is the exact sum of the requested range. By storing the running totals ahead of time, we replace a slow, repetitive counting task with a single subtraction. The memory access is immediate, regardless of how wide the date range is. Let's jump into the IDE and write the initialization function in C++ to build this array. We will call it build prefix. This code block shows our function structure. The very first thing we add is a safety check to verify if the incoming data vector is empty. If we skip this check and pass an empty array to our function, our code will blindly attempt to access the 0 index. That triggers a segmentation fault and crashes the program. Once we confirm we have data, we allocate our new prefix vector. We then set the first element of our prefix vector to exactly match the first element of the incoming data array. Next, we write a single for loop starting at index 1. It iterates through the rest of the array, adding today's value to yesterday's cumulative total, and stores the result. We pay a minor cost in memory allocation to run this loop once during startup. In exchange, we protect the application's runtime performance from linear delays when users are actively clicking around the interface. Now we write the query function that users will actually trigger. We will call it getRangeSum. It takes 3 parameters: our pre-built prefix array, the left boundary of the requested date range, and the right boundary. This diagram shows the core of the function. We return prefix of r minus prefix of l minus 1. There is no loop here. It is a single, constant time operation. However, this single line contains a logic failure known as the 0 index trap. We have to consider what happens if a user requests a range starting at the very first day of our dataset. If the left boundary is 0, our math tells the computer to look up 0 minus 1. The program searches for index -1, which does not exist, leading to a memory access violation and an immediate crash. To fix this, we insert a conditional statement right above the return. If L equals 0, we return prefix of R. This intercepts the request and directly returns the total up to the right boundary, completely bypassing the subtraction. Writing resilient code means understanding the mathematical path and structurally locking down the memory boundaries before a user request pushes the system out of bounds. This architecture eliminates the processing bottleneck entirely. When applied to the dashboard, a complex date query that previously locked up the browser now immediately resolves with instant data delivery. The complete tested C++ source code for these functions is in the video description below. If you found this breakdown helpful, leave a like and subscribe to the channel. Designing for constant time lookups allows systems to remain responsive under heavy load, ensuring that server stability is never sacrificed for query flexibility.